Hey, welcome! Today, we are digging into the elegant, invisible rules that run our entire universe. We're going to see how the exact same principles that decide a simple race down a ramp can also explain the incredible, majestic spin of a galaxy. And believe it or not, it all starts with a simple little puzzle. So here it is. Picture this. You've got a solid sphere and a hollow cylinder. They have the exact same mass, the same size. You put them at the top of a ramp, side by side, and you'll let them go at the same time. Who gets to the bottom first? Now, the answer here is probably not what you'd guess, and figuring it out actually reveals a really fundamental truth about how everything works. To solve our little race, we first have to understand how the universe balances its books. Seriously, think of it like a bank account. But the currency here isn't dollars, it's energy. And this bank account has some very, very strict rules. Okay, so first up is what we call potential energy. In our bank analogy, this is like the money you've got saved up. It's just stored value, energy an object has just because of where it is. So, our racers at the very top of that ramp, they have a full account of potential energy, just waiting to be cashed in. The other side of this is, of course, kinetic energy. And this is the energy you're actively spending. It is the energy of pure motion. As soon as something starts moving, it's converting its potential energy into kinetic energy. If an object is just sitting still, its kinetic energy is zero.
Now, here is the single most important role of this cosmic bank. In what we call an isolated system, which is just a fancy way of saying no friction, energy is conserved. It can never, ever be created or destroyed. The total amount in the account always stays the same, it just moves from one type to another.
So let's go back to our racers. At the starting line, they're not moving, right? They're just sitting at the top of the ramp. So their entire energy budget, 100% of it, is potential energy. They have zero kinetic energy because, well, they haven't moved an inch yet. But as they start to roll, they begin cashing in that stored potential energy. They're making a withdrawal and converting it directly into the energy of motion. That's the kinetic energy. By the time they're exactly halfway down the ramp, their energy account is perfectly split, 50% potential, 50% kinetic. And when they finally cross that finish line at the bottom, their potential energy account is totally empty. It has all been converted into kinetic energy, and that means they've hit their absolute maximum speed. But that just brings us right back to the puzzle, doesn't it? If both the sphere and the cylinder start with the same energy and end with the same energy, why would one of them win the race? Well, the secret lies in the fact that not all motion is the same. You see, motion isn't just about moving from point A to point B. That's called translational motion. And yeah, our racers are definitely doing that. But they're also doing something else at the same time. They're spinning. And this second type of movement, rotational motion, is the key to everything.
Now, to get a handle on this, we don't have to learn a whole new set of physics. Not at all. We just need to learn a new dialect, you could say. We need a way to translate the language of straight line motion into the language of spinning motion.
And what's so cool is that we have something like a Rosetta Stone for this. For every single concept in straight line motion, there is a direct equivalent for spinning. So linear velocity becomes angular velocity. A push or pull, a force, becomes a twist, which we call torque. And mass? Well, mass has a rotational counterpart. And this is the one that solves our puzzle. That counterpart is called rotational inertia. It's basically a measure of an object's resistance to being spun, how much it hates to start spinning. And here's the crucial part. It doesn't just depend on how heavy an object is, but on where that mass is. The farther the mass is from the center, the harder it is to get that object to rotate. So this brings us right back to our energy bank account, because it turns out there's a kind of hidden fee that we haven't been talking about yet, a hidden energy cost that comes from the act of spinning itself. We're already familiar with the cost of just moving forward, right? This is the classic formula for what we call translational kinetic energy. It's all about an object's mass and its velocity. But a spinning object has its own separate kinetic energy. And just look at that formula. It's almost identical. Instead of mass, we have rotational inertia. And instead of linear velocity, we have angular velocity. This is the energy cost just for rotating. So for any object that's rolling, the total potential energy it started with has to be split. Some of that energy budget goes into moving the object forward, and some of it has to be spent on making it spin. It has to pay for both kinds of motion. And there it is. That's the solution to our race. The hollow cylinder has all of its mass on the outside, far from the center. That gives it a really high rotational inertia. It has to spend more of its energy just to get spinning, and that leaves less energy in the budget for moving forward, which makes it slower. The solid sphere, with its mass more concentrated in the middle, has a lower rotational inertia. It's cheaper to spin, so it can spend more energy on speed. The solid sphere wins.
Now, this whole idea that rotation plays by its own set of rules, it scales up to one of the most powerful and fundamental laws in all of physics.
It's called angular momentum. If you think of regular momentum as how hard it is to stop something moving in a straight line, then angular momentum is how hard it is to stop something from spinning. And just like energy, if there are no outside forces, the total angular momentum in a system is always, always conserved. The best way to see this is with a figure skater. You've seen this, right? She starts spinning with her arms stretched way out. With her arms out, her mass is spread out, far from her center. This means she has a very high rotational inertia, so she spins pretty slowly. But then, watch this. She pulls her arms in tight to her body. All of a sudden, she's brought her mass closer to the center, which dramatically decreases her rotational inertia. Since the universe demands that her angular momentum has to stay the same, it has no choice. Her spin speed has to skyrocket to balance the cosmic equation. It's amazing to watch. Okay, so let's wrap up with the key takeaways here. First, and most importantly, energy is always conserved. It just changes its form. Second, for things that are rolling, they have to split that energy budget between moving forward and spinning around. Third, we saw how every concept in linear motion has a perfect twin in rotational motion. And finally, the big one, how an object's mass is distributed, its rotational inertia, is what decides how it moves and spins. It's the key that decides who wins the race. And that leaves us with a final kind of mind-blowing thought. The exact same principle that makes a solid sphere beat a hollow cylinder down a ramp, the same law that lets a skater spin incredibly fast, is what keeps our planet locked in orbit and our entire galaxy spinning in this beautiful cosmic dance. We can see this law everywhere, from the smallest toy to the largest structures we can imagine, which leaves us with one really big question to chew on.